Let's talk about solving series that are not regular. If you have series where the first term, the coefficient of y double prime, is not something you can easily divide everything by because it becomes 0 in the range of x. We usually take the range of x, if it's not mentioned, to be all of the real line. Then you cannot divide both sides because you cannot divide by 0. So if you have this embarrassing situation, then our previous methods cannot be used. What we have to then do is seek a solution of the form y of x equal to x minus x naught to some power, which I'll call sigma, and then proceed to find the usual series sum. So an x minus x naught to the power n, with the understanding that a naught is not 0. If a naught is 0, then it'll undermine this coefficient sigma. So the sigma is there precisely to protect you from any blow-ups at places where p naught x is equal to 0. This is called the Frobenius series or the Pursot series, and this theorem can be found in most ordinary differential equation books. I'm not going to prove it, I'm just going to use this result to solve problems. A particular differential equation that we can try to solve is x squared y double prime minus 6y equal to 0 with some unspecified initial conditions, which I will not worry about. Now you notice that p naught in this case is the function x squared, and x squared equal to 0 gives me x equal to 0. There's a double root there, which means that we have to seek our solution. Make no assumptions about sigma to start with. Always choose a solution to be of the form indicated here. In this case, x naught is equal to 0, so we can also additionally write x naught equal to 0 here. That's a singular point. So this gives us our ansatz to be y of x equal to x to the power sigma times sigma n equals 0 to infinity an x to the n. You can bring the x to the sigma inside. Even though it's not a function of n, it can be brought inside. So I get n equal to 0 to infinity an x to the n plus sigma. Now you proceed exactly as you did for the regular series method. So y prime is going to be the sum from n equals 0 to infinity. Observe, I don't shift the summation index because sigma is no longer 0. I don't have to worry about shifting it to n equals 1. I keep it as n equals 0 itself. N plus sigma an x to the n plus sigma minus 1. And then y double prime will be equal to sum from n equals 0 to infinity of n plus sigma times n plus sigma minus 1 an x to the n plus sigma minus 2. So it all looks pretty complicated, but it really is not. It's just following procedure. So the original differential equation, x squared y double prime minus 6y, simply becomes, if I take y double prime and multiply it by x squared, the 2 term goes away. So I'll just get an x to the n plus sigma. And 6y also has only n plus sigma. So I'm in luck. There is no odd term running around. So n equals 0 to infinity. Putting everything together, I just get n plus sigma times n plus sigma minus 1 minus 6, because of that 6 here, times an x to the n plus sigma is equal to 0. Now the only way for this to be satisfied is for each value of n to satisfy that. So what I'll do is I'll take n equal to 0, the n equal to 0 term. the n equal to 0 term as a coefficient of x to the sigma. So essentially I'm comparing the coefficients of x to the sigma on both sides. Well, clearly the coefficient of x to the sigma here is 0. So I can get, with x to the sigma comparison, that's only possible for n equals 0. That's another way of saying that, well, of what you're doing is set n equals 0. So I get sigma times sigma minus 1 minus 6 a naught x to the sigma equals 0. Now clearly we have chosen a naught not to be 0, so we cannot use that option. We are forced to conclude that the following quadratic equation must be satisfied, and that is sigma squared minus sigma minus 6 equal to 0. And this gives us, using FOIL, two solutions, sigma equals 3 and sigma equals -2. Now these are sometimes called the characteristic exponents of the differential equation. So there are some, easy ways of getting some practice. Once you do this enough, if you have differential equations like this and you have -6, you can immediately see that -6 is 3 times -2. But I would urge you not to go in that direction. I can see these things more easily after doing many problems, but you should always proceed systematically. That, by the way, what I said is not even true if you have y prime and things like that. So avoid the temptation to look at the differential equation and start predicting what the characteristic exponents will be like. Now, for each characteristic exponent, you have a separate life history. So we're going to have to deal with each one separately. So let's look at sigma equal to 3. Now for values of n other than 0, you're going to get n plus 3 times n plus 2 minus 6 an equal to 0. You cannot choose an to be 0 because, well, it could be that an equals 0. Let's see how this plays out. So this gives me n squared plus 5n minus plus 6 minus 6 times an equal to 0. Remember that n is not equal to 0 in this case. The 6 cancels out, and I end up getting n times n plus 5 times an equal to 0. So we have two options, either n equals 0, which is not allowed, or n equals minus 5. But n is not minus 5. The summation starts from n equals 0. So we are out of luck. This entire branch, sigma equal to 3, is excluded. Let's look at the other branch, sigma equals 2. Minus 2 actually. Then I'm going to end up getting n minus 2, n minus 2 minus 1, which is n minus 3, minus 6 an equal to 0, which leads me to the same type of thing, n squared minus 5n, however, plus 6 minus 6 an equal to 0, and this time you have n times n minus 5 an equal to 0. We are in luck. N cannot be 0, but n can be equal to 5. So we this way we are led to the solution of this differential equation. So what we're going to do is take the n equals 5 term. Y of x then is just going to be x to the sigma, which in this case is minus 2. We're going back to this ansatz here, the Frobenius ansatz. X to the minus 2 times the sum from n equals 0 to infinity an xn simply reduces to x to the minus 2 times a naught, which is never 0, remember that. And then you have the fifth term, a5 x to the 5. And that's it. The a0 and a5 are got from the initial conditions, which I did not state. So the two solutions are going to be a0 x to the minus 2, taking the x to the minus 2 inside, plus a5 x cubed. It's now a trivial matter for us to verify that these indeed satisfy the original differential equation. So let's take a couple minutes to verify that. Let's take the first derivative. That's y. Y prime is going to be negative 2 a0 x to the minus 3 plus 3 times a5 x squared. And then y double prime is what we are really after, because the differential equation does not even have a y prime in it. So y double prime is negative 3 times negative 2, or 6 a0 x to the minus 4 plus 6 a5 x. And the differential equation says x squared times that. So x squared times y double prime. Let's see if that's equal to 6 times y. If we find that x squared times y double prime is equal to 6 times y, we have satisfied the differential equation, because one way of rearranging the differential equation is to move the 6y to the right hand side and say x squared y double prime is equal to 6y. So let's find out if it's indeed equal to 6 times y. X squared times y double prime is 6 a0 x to the minus 2, and then x squared times this term here is 6 a5 x cubed, and you notice that it's indeed 6 times y. So we have managed to find the unique solution to this differential equation.